Okay, so the noon class, we got through them all. So, and we're one question ahead of the noon class, so I think we'll get through them all. Tend to go faster this class anyways. Does anybody have any questions about anything before we start? No class on Monday, so this is the last class. So next week is finals week. What's that? You're just like, thank God. That's cool. All right,
It
so
just went by really fast.
I don't know. It's been a long semester for me. So, all right. So get the wavelength, and you'll be given these equations. Speed of light is frequency times wavelength. I'm sorry. Get the frequency. So that means frequency is speed of light over wavelength is 3 times 10 to the 8 meters per second divided by 632.8 times 10 to the minus 9 meters. And put that in your calculator. 88 divided by 632 minus 9. This is 4.74 times 10. Oh wait, that's not the minus. 10 to the 14th. 1 over second. 1 over second is also known as a hertz. And then the energy is h times the frequency equals 6.626 times 10 to the minus 34 joules times seconds times 4.474 times 10 to the 14. This is 3.14 times 10 to the minus 19 joules. So you're given all the equations and all the constants, but why don't you go ahead and try part B. Is anyone getting stuck? I didn't know if you were running off that. I'll be right back. Okay, good. So everyone got this one? These are pretty easy, but let's review. So anybody have any questions with this? Okay. That's done. Okay. So this one I'm just going to kind of explain. So the possible values of L for each value of n. So the first one, if n is 1, L can be up to n minus 1. So if n is 1, L has to be 0. For n equals 2, L can be 0 or 1. For n equals 3, L can be 0, 1, or 2. And for 4, L can be 0, 1, 2, or 3. Right? You guys got that? Okay, and then which set of quantum numbers cannot specify an orbital? So, and there is a question like this on the final. So n is 2. That means L can be 0 or 1. 1 is fine. If L is 1, M sub L can be minus 1, 0, or 1. Minus 1 is fine. Okay, so B, n is 3. L can be 0, 1, or 2. 2 is fine. If L is 2, M sub L can be minus 2, minus 1, 0, 1, and 2. 0 is fine. For C, n equals 3, L can be 0, 1, or 2. L is 3 is wrong. C is bad. D, n is 4, L can be 0, 1, 2, or 3. 3 is fine. If L is 3, M sub L can be minus 3, minus 2, minus 1, 0, 1, 2, or 3. 0 is fine. So, questions with this one? But it's something straightforward. Okay. It's probably what you guys are after. Write the orbital diagrams for each ion. Indicate the ion is diamagnetic or paramagnetic. I guess I should. I was jumping back and forth before, but then again, the screen keeps on disappearing on me. So I will just go and circumvent that by taking a picture of the periodic table. Okay. Actually, maybe I'll make it bigger. A little bit bigger. Okay. So vanadium. Vanadium is here. So write orbital diagrams and indicate whether the ion is diamagnetic or paramagnetic. So diamagnetic means that everything is paired up. Paramagnetic means that there's one or more electron that's unpaired. So vanadium structure. So just plain old vanadium. Vanadium structure is argon structure. And then over here, this is 4s. 4s2, 3d3. Okay? Oops. So do you see where I'm getting that? So vanadium is right here. It gets the noble gas configuration of argon. This is 4s, 1s, 2s, 3s, 4s, 3d, 1, 2, 3. Okay, so that's vanadium atom. So vanadium plus 5, this is going to rip off the electrons. I'm just kind of putting zeros there. Rips off those 5 electrons, which is neons. It's argon's configuration, which is neon. 3s2, 3p6. And since the diagram, if you will, it'll be like this. Like that. And in a question like this, you'll be given any sort of diagram, so you're not having to memorize the relative energies of the electrons. Okay, I'll do one more. Chromium plus 3. Chromium is right here. So chromium's plain old structure is argon's. 4s2 3d4 because it's 1, 2, 3, 4 across. So, and then is it plus 2? Is it plus 2 or plus 3? Plus 3. Plus 3. When the electron is ripped off, it's ripped off the highest end first. So it's going to be 4s0. I guess I'm doing this for emphasis. 3d3, which really it's just going to be argon 3d3, like that. So it rips off the electron there. Then a diagram, 3d, it's going to be 3 electrons put up like this, and this is in fact paramagnetic. So the 3D orbitals, they're known as degenerate, or meaning same energy level. And when you have degenerate orbitals, the electrons add one at a time with parallel spins. That's known as Hund's rule. So that's like also if you're in the bus, that's sometimes called the bus seat rule or the swim lane rule. So if you swim, I like having my own lane in the pool. So if I'm first at the pool, I get my own lane, and then if someone else comes to the pool, he or she would go in his or her own lane. Normally wouldn't get in my lane. I'd be like, hey, what are you doing in my lane? You know, there's open lanes over there. Or if someone got in my lane, I would probably move to an open lane. Because an electron's the same way. They're negatively charged. They don't like being around other electrons. They'd rather have their own lane, have their own orbital. So, okay. So there's that one. How are we any other questions with this? And the unpaired electrons means paramagnetic. So why don't you do it for iron plus 3. So iron plus 3, and here is iron. Ha, got one student email me already, and one from the course evaluation systems. That doesn't count. I was saying at least 4 students will email me during class. That's my guess. Anybody have another bet? Maybe not. So what is iron? Iron is argons, 4s2, 3d, 1, 2, 3, 4, 5, 6. So plus 3, it's going to lose the 4s2 first, and then 3d5. So 3d5, and then 5 electrons, all parallel spins. So it is definitely paramagnetic. So Does anybody have any questions on how to do this? Is this making sense? I know I'm not really going around, but please ask. Anybody confused about something? Do you want to do another one? Or is this good? Yes, James.
So for the vanadium,
Vanadium? Yeah. It's diamagnetic.
yeah. So when we did the +5, it took off the electrons in all of them. It took off the ones in the 4s and 3ds.
Yeah.
So what is there now? Is 3s?
That's argon's configuration.
Oh, okay. Okay.
Yeah. And they're all paired, so this is diamagnetic. Other questions? Okay. Alrighty. So, isoelectronic. This means same number of electrons. So if we look at these ones here, so decreasing radius. So if you look at these species, so they all have 10 electrons. The difference is oxygen, so the elements always retain the number of protons. So an O-2 ion oxygen atom has 8 protons and 8 electrons. I know 6 valence, 2 core, but when you add 2 electrons to it, the O2 minus, it still has 8 protons, but now it has 10 electrons. So these all have the same number of electrons, but oxygen has 8 protons, fluorine has 9, sodium has 10, and magnesium has 12. And the more positive center is the smaller ion. So magnesium, it's the tightest, it's the smallest, so that plus 12 center can draw in the 10 electrons pretty tightly. Sodium's a little bigger, fluorine's pretty big, and oxygen's just huge. Or oxide, I should say. Oxide is huge. So this is the size. The size trend is this way. Oxide greater than that, greater than that, greater than that, because of that. So try that for the series selenium, strontium, rubidium, and bromide. And they all have 36 electrons. With this, you should probably be able to logic your way through it. If it's isoelectronic, you know that the negative ions are going to have, since they all have the same number of electrons, the negative ions are going to have more electrons than protons, and the positive ions are going to have more protons than electrons. So in this case, you write it out, and like if you look at the periodic tables, just like like strontium. So strontium's here. It has 38 protons, rubidium has 37. So the number of protons doesn't change. So, and then this way, the size trend will be as such. So, does this make sense? Questions with this? Okay, I need to get another picture of the periodic table. Actually, do I have it in my photos? There we go. So bromine or bismuth. Okay, so when you do first ionization energy, the trend is this. Up and to the right is positive. So if you go up in the periodic table and to the right, that is the positive direction. And actually, maybe I'll start over here. Sodium and rubidium. Sodium is over rubidium. Therefore, this is the one that has the higher first ionization energy. So the green one here, phosphorus and tin. So phosphorus is up and is to the right. Just like bromine and bismuth, bromine is to the right and it's higher, so bromine is the higher first ionization energy. You will not be given an ambiguous one, meaning, and one of the questions on there was ambiguous, I don't know, am I British or something like that? I was watching something about Benedict Cumberbatch before I came to class. The other one was acetine and arsenic, and this one's ambiguous. So that's not fair. Okay, so let me put some other ones. So I'll erase this and phosphorus. That's not a fair one. Phosphorus or indium. Silicon or chlorine. Hopefully you're not colorblind. If you are, I do apologize. Maybe instead of the blue, maybe I'll move the blue one up here. Just so it's not. How about the red, thallium or aluminum? Which one's higher? Aluminum, it's higher. It's above thallium. How about the green, silicon or chlorine? Chlorine, right? More for the right. What about the blue, antimony or nitrogen? Right, nitrogen's higher. What about the orange, indium or phosphorus? Phosphorus, right? It's both up and to the right. So, you guys got this? Okay. Another question here. Yeah. Okay. So formal charge. The way formal charge works is you get half of the bonding electrons in all the lone pairs and compare it to the original. So carbon originally has 4 and sulfur originally has 6. So when you look at carbon here, it has 4 and it originally has 4, so this is a formal charge at 0. If you look at sulfur, sulfur has 6 electrons. It originally has 6. It has a formal charge of 0. Over here, sulfur originally has 6. It has 4. It has a formal charge of +2. And carbon originally has 4. Now it has 6. It's got a formal charge of -2. And because of that, the better molecule is the first one because it minimizes the formal charge. So, does anybody have any questions on how to do this? All right, try her out here. I guess a little bit on the screen, but my iPad, that green color is really bright. It's the color we see the best, actually, this fluorescent green. So that kind of gave you the answer. Does anybody have any questions on how this works?
How many valence do oxygen and silicon have?
Oxygen and silicon?
Oh, sulfur?
Sulfur has 6. It's underneath oxygen.
I mean,
So
oh. Okay, right.
sulfur.
Looking at oxygen and silicon.
Sulfur's right there. So it's group 6A. So 6 valence.
Okay.
Silicon has 4. It's underneath carbon. Other questions? There you go. All right, so other questions students had on this. You do not have to memorize any of the bond energies that will be provided to you, and it'll be a much abbreviated table, unlike this one. This one is very detailed. I'm just going to go ahead and make it small, because we only need this part anyways. Okay. So the way I do these is I just go out and draw the entire thing with Lewis structures. So I even get the numbers in there too. Oh, I have 2 CO2s, too many CO2s. So the delta H is equal to the sum of the bonds broken minus the bonds formed. So the bonds broken, we have 5CH bonds and so 5CH bonds plus 1CC double bond, single bond plus 1C oxygen single bond. And if you are colorblind, I do apologize. I'm trying to color code these to make it easier. Oh, I missed the color ones. Okay. What color haven't I used? I need orange. Oh wait, I already have it. I already picked one for red. This is a pretty long one, but you go and you pick out, you find all the different bonds that you have. You write the Lewis structures for both sides, and then you look at the ones you've broken, and then you subtract the ones that you formed. And if you want, you can get rid of this one OH and put 5 over there. That's the other thing you can do. But then you just find the numbers on the chart and put them in. This is kind of a longer one. But here's an easier or quicker one. It's more like the one you'd have in the final. And I'll go ahead and give you the Lewis structures for these. So carbon plus spider web. We think the spider expected to catch that. I dropped myself down. Not very edible.
Yeah, yeah.
Okay. Yeah, this is a one. Yeah, that's something. Yeah, that's something. Because then I mean, yeah, because then you're gonna have 6 carbon hydrogen bonds in there.
Oh, so it's 2 sets of these.
Yeah. Oh no. I mean, that molecule is gonna be.
Okay.
So it's 6 carbon hydrogen bonds and then the carbon carbon 2 bond.
Okay, cool.
Yeah.
That's just 2 different kind of separate 2 carbons.
Yeah. That's nothing down there that we did more explicit. So this has to be confused. There you go. You good? You tie-dye today? No. All right, everyone seems to be getting any questions with this. It'll be, number 82 is a pretty difficult one, but I just went ahead and drew it all because, kind of fun. I gotta play with the colors too. But 83 is more likely because they're short and quick. Man, we're flying by. Okay. So the hybridization, if you saw the given information I'm giving you guys, right? So what you are going to get is this chart. So you're getting the Vesper chart. And you are also getting this chart here with the electron geometry, so whatever it is, the number of electron groups, electron geometry. So you get that. So, and I'm going to focus on the carbon centers. So if you look at this carbon has 3 groups, which means this is planar electronic geometry, which means sp2. So linear is sp, planar is sp2, and tetrahedral is sp3. So if you look at this carbon center, it has 4 groups, which means tetrahedral or sp3. If you look at that carbon center, it has 4 groups, which is tetrahedral or sp3. So, questions on how I'm doing this? Okay, why don't you do it for these 3. See the atoms, I mean, it's all carbon, but and it's going to be carbon on the final, but the atom's identity doesn't really matter.
So we're identifying the shapes of
Well, specifically electronic structure. So,
Yeah.
So, the blue one here, it has 3 groups.
Yeah.
Right, so 3 groups means planar and this one. Okay, so this one here, it has 4 groups. Right, so one hydrogen, hydrogen, carbon, carbon, so 4 groups. That's tetrahedral. This one here has 3 groups. And it doesn't matter. It doesn't matter which group it is. I mean, so like it could be. It's like nitrogen over here has 4 groups: hydrogen, hydrogen, carbon, and one there. So it's but it's going to just be carbons.
Okay. Yeah.
check it out.
Yeah. I didn't see the check.
This is check time.
Okay, cool. Yes, I understand now.
You understand?
Yeah.
You sure?
Yeah. Do you us the given?
I don't have that on me. It's in the email.
Okay.
Do you want to know what I just showed you before?
Well, no, yeah, but you were potentially doing, is it gonna be,
You will be given.
there's also part of,
You're given this chart.
yeah, that's what I'm asking.
And if you look at the email, I basically chop off this part. And it's this stuff. And
Okay,
then,
and
then I also give you this chart.
this is what we're doing right now.
Yeah.
That's
Yeah.
what we're doing right now.
Yeah, the electron, so like the number of electron groups, the geometry, and then the hybridization.
Okay, so you, oh, okay, you didn't try.
I didn't put the trigonal.
And if it's tetrahedral plan, we have to associate that with the
Wait, what's this tetrahedral on the side?
trigonal.
Yeah, you have that.
And then do we have to use that with the other given?
Not necessarily.
Okay.
No, because this just 3 electron groups means planar, trigonal planar geometry, which means sp2, which means bond angles about 130 degrees.
And then these other ones separate.
Yeah, you can use this one for molecule shapes and also for polarity. Because then I also give you this chart, the black and white.
Okay.
Do you check your Gmail?
Yeah.
I should have. I sent an announcement.
Okay.
So it has the given information here. I shared it with everybody. You guys have the email, right?
What you said,
The exam key?
please?
I hope I didn't send it out.
You did the test too.
Oh yeah, I did that.
Which evaluation?
If you just want to leave on order announcements, it's okay.
Yeah, but anyways, that's where it is. I show you everything you're getting in the test. What do you get?
Yeah.
Any question?
Everything good.
Okay. Okay. So last one. So a single bond is a sigma bond. A double bond is 1 sigma 1 pi, and a triple bond is 1 sigma 2 pi. Maybe I should use something other than equals. There we go. So every single bond is just a sigma bond. A double bond is a sigma bond and a pi bond. A triple bond is a sigma bond and 2 pi's. So I guess this is kind of like what you mentioned with the homework. This CH3 is actually carbon, hydrogen, hydrogen, hydrogen. So this here, so there's 3 for each of these H3s and then the one with the CH. This is 10 sigma bond, and then each other bond is a sigma bond as well. And then I'll do the pi bond. So, very colorful. All right, so 3 here, 3 there, and 1 here. So that's 10. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Did I count them all? So that would be 25 sigma, and then 4 pi bonds, because each double bond is a sigma bond and a pi bond. Let me make sure. So, yep, 25. Got it. Again, as long as I'm counting, not counting incorrectly twice in a row. Okay. So does this make sense that counting the pi bonds and sigma bonds, all single bonds are just a single sigma bond. A double bond is 1 sigma and 1 pi. So you count every single one of the bonds for the sigma bonds. We got 25 bonds there, plus the double bonds. So there's 4 double bonds, so there's 4 pi bonds. Okay. Let's see if we can do it for aspirin. And again, this is really let's put the line there. Feel like I'm playing a counting game. Well, yes, it is a counting game. Although I kind of put the answer on there already. Is anybody confused about anything? So that's actually all that I have prepared. So we're done 20 minutes early. And I have a message from my chair. The department head asks you to fill out the student evaluations. He asked me to offer extra credit, which I already have. And
Did we get it?
what's that?
Did we achieve it?
We're about 50%, but the truth of the matter is I was going to give it to you anyways.
Oh.
Because that's just begging to be, that's about 2/3 of the class right now. And I said 75%, but that's good enough. But I'd like to see everyone do it. But, and the department head also asked you to register for your classes for the spring semester. So, so it's also discussed, people tend not to register until after the purge date, which is the 14th of December. You guys typically do that? Is that what you do? No, you don't? Okay. You just register anyways? Or do you? Oh, you did? Okay. Yeah. So, so I'm teaching 3 sections, 161, and actually all 3 sections, you guys have been amazing. I've really enjoyed having you guys as students. You guys have done very well. So I've been teaching for 13 years. So hopefully it's been a good experience for you too. So of course, maybe you'll change your mind after the final. I don't know. So we got 15 minutes left. So you guys are free to go. But do you have any questions? Hopefully, I mean, we spent like 4.5 hours reviewing for the final. So